Christine.
Hi, Christine. Hope you're doing well. So here we are taking a look at the last example of the day. We've got a mass weighing 8 pounds. It stretches a spring 2 feet. You know, right here, I look at that part and I think, wow, I'm thinking of Hooke's law. You know, as we can definitely come into play. What was Hooke's law all about? Well, we could say it was that the force was equal to some constant times the distance. And force is really weight. So we've got 8 pounds of force. We've got 2 feet. It doesn't take too long to see that, you know, K is equal to 4. Well, we also have this situation. We need to find the mass as well. And again, the first thing that you should think about is, you know, Newton's law, F equals ma. You know, what you really have is weight is equal to mass times the gravitational constant. So you've got 8 pounds of weight. Your mass right here and the gravitational constant when we're in the customary units, that would be 32 feet per second, right? And very quickly we could divide by 32 and we'd get m is equal to 1/4. Do you guys remember the unit there? The slug. Yeah, that sounds so funny when we've got that, right? Okay, so we've got our m and we've got our k. But here's something that you definitely could, you know, remember. As we read through this a little bit more, it says, assuming that a damping force numerically equal to 2 times the instantaneous velocity. What that's going to tell you immediately is the constant involved with the damping force is 2. It's actually telling you that beta is equal to 2. Okay? You might remember what omega squared was. Omega squared was, you know, k over m. And wow, we've already found that k was 4 and, you know, m was 1/4. Divide by 1/4, it's the same thing as multiplying by 4. You'd get, you know, 16. And then, of course, you might remember what 2 lambda was. 2 lambda was beta all over m. And where are we getting all of that from? Well, that's just by, you know, definition, of course. Your beta is, you know, a 2, and your mass was, you know, 1/4. And so that's going to get you an 8, right? So 2 lambda is equal to 8. That also means that lambda itself would equal 4. And I think sometimes kids even question why I'm even going in that direction. I'm going in that direction, guys, maybe just to point out to you the big question of what we've been looking at. What's happening when we've got lambda squared minus beta squared? Well, lambda squared, of course, is going to be 16. And, you know, all of a sudden kids will look at that. They'll say, well, my gosh, and forgive me, I did lambda squared minus beta squared. What did I mean to write? Lambda squared minus omega squared. My apologies for that. We'd have 16 minus 16. So that's going to be 0. What am I checking right now? I'm trying to say, hey, are we overdamped? Are we critically damped? Or are we underdamped? Well, what do you think? This is critically damped. Just in case you were ever asked to do that. You know, we have to look at lambda squared minus omega squared. If it's positive, that means that you're overdamped. If it's 0, you are critically damped. And if it's negative, of course, you are underdamped. So from the very get-go right here, we know we're in a critically damped system. Now, what you can do to help yourself out, you're just setting this thing up. You know, of course, we could have just this general second order differential equation. You could, of course, leave it as 2 lambda dx dt plus omega squared x. But I think very often we actually jump to this one. It's all going to be the same at the end of the day. I think we'd all agree. So what does our second order differential equation really look like? Well, we've got our beta. We already found beta was a 2. So we'd say that's 2 all over m. And of course, we found our k over m. Wow, that was actually, we found that was 16, right? And so it doesn't take too much, hardly takes anything at all to get to your differential equation. Now, there is something else that remains to be discussed. We'd like to see what our initial conditions are. We are going to solve this, and we are going to also try to find our constants. So let's go back to the problem here. And, as we read through this, it says, determine the equation of motion if the mass is initially released from the equilibrium position. That little phrase right there tells you something. Yeah, x of 0 equals 0. That's the equilibrium position when x equals 0. Now, it says, then you're going to have an upward velocity. So velocity is x prime of 0. We're going to say x prime of 0, it's an upward velocity of 3. So x prime of 0 is negative 3. Remember, downward is positive, upward is negative. So, wow, let's put those two initial conditions next to our problem also. We've got x of 0 is 0, and x prime of 0 was negative 3. And guys, at this point, I could have given you this problem last chapter for sure. We're just dealing with the specifics and solving here with these, immediate applications. We'd get a characteristic equation of m squared plus 8m plus 16. Hey, that factors, what does it factor into, guys? M plus 4 and m plus 4. And guess what solutions we have? M's equal to negative 4 and m's equal to negative 4. Wow. So imagine that you saw this a ways back. What would our solutions look like? C1 e to the negative 4t. Remember, t is our independent variable. Oh, be careful. Yeah, c2 t e to the negative 4t, right? X itself is our position here, and our independent variable, what we normally have used as x, is actually a t. Okay? We doing okay so far? All right, so the only thing that remains now is to find out what our C1 and our C2 would actually equal. I could go ahead and plug in my initial condition. I could say, look, you're going to be at position 0 when you plug in t equals 0. So, wow, plugging in a t of 0 in that second solution is really nice. I'll tell you why. That t out in front is going to come to our aid. That's going to wipe all this out. 0 times anything is going to go away. And then you can pretty much real quickly see that this e to the 0 is just a 1. So C1 is equal to 0. Wow. So we're at a point right now where if you wanted to, you could even plug that in immediately. You could say, if you'd let C1 equal 0, this whole thing right here just cancels out, and then you're left with C2 t e to the negative 4t. Okay, so that's helping us out some. We're at a point where we can say, I know for this problem, that first part essentially just completely drops out. Your C1 is just gone. But then we'd say, well, wait a minute. We've got x prime of 0 equals negative 3. We're going to try to plug in a derivative. So x prime right here, we're going to have to do a chain rule. Not a chain rule, a product rule, right? You can take C2 out in front if you'd like. And you'd say t times, well, here we'd get negative 4e to the negative 4t plus, then our derivative of our first function here is just a 1. Here's e to the negative 4t. And you could say, well, there you have it. Now, you could try to clean some things up, but my suggestion is let that derivative equal negative 3 and just plug in your t of 0 immediately, because real good things happen then, right? Wow, you can see already what's about to happen. This ugly part is just completely gone. E to the 0 power is just going to be a 1. And guys, you'll get C2 to just equal negative 3. Look at that. So right here we can wrap up and say, hey, before we knew that x was equal to C2t e to the negative 4t, so it's negative 3t e to the negative 4t. And that, guys, is what your equation would actually look like if you were to even graph it. Graphing it could be an interesting kind of a situation, too. That's definitely worth talking about as we're looking at critically damped systems here. Look, really, on the left side, we'd want this. You can see we've been working in polar in calculus. So I'm just going to hit second quit, clear this, and go up here and type in negative 3. My t is kind of like my x. And why am I doing this? I just want to show you guys what this motion would really look like. See, x is, our position, but it's the dependent variable here. Normally, that's what we call y. T is our independent variable. It's really what we think about with x. And, you could go ahead and maybe do a zoom decimal and see what's going on. And you could see that, it looks like it's going to start off from position 0. Hey, maybe we could even, get a better viewpoint here. It's not moving much, is it? It's definitely not moving much. Maybe we could divide this by 2, divide this by 2, and just get a better view as to what's happening at this motion of the spring. You can see it's definitely critically damped. You would expect for it to make a sine wave or a cosine wave, but something is impeding that. It's going to really be asymptotic with that x-axis, which is the equilibrium position. It's going to come to that equilibrium.